All right, now let's examine how we can implement a data structure. So, great data structure, fairly easy to butcher and end up with something unusable. So let me define some terms for you before we start implementing. We'll start with U. That's going to be the universe of all possible objects. So all possible objects that we want to store in the hash table. So let's say we're storing IP addresses, it would be all possible IP addresses. If I want a hash table with all my students in it, it would be the student names. That's probably what I would use, or student ID numbers. If we're trying to solve the game of chess, then it would be chess configurations. That's U. The list of all possible things we could put into the hash table. What we really care about, though, is some subset, S, of the universe. So I don't care about all IP addresses. I just want to store some subset that's a reasonable size. So thousands, hundreds of thousands, millions, but not all. So I want to store some subset of the entire universe of data. One naive solution on one end of the spectrum is just to create an array equal to the size of the universe and just have an individual slot for example, every IP address. Well, if I'm going to store just 1,000 IP addresses, I probably don't want to have a spot for all possible IP addresses, which would be something like 255 to the 4th power. Well, on the opposite end, that would create no collisions, but we need to use a huge amount of space for our underlying array. Naive solution number 2 is to use a linked list instead. So in that case, we only have to store we only need one slot for each thing we want to store, but now we basically have a collision for everything. We're just storing everything in the exact same linked list, so we're not going to have constant time lookups. So we usually do something sort of in between these two approaches. So let's say we have a hash table. We want n to be approximately equal to the magnitude of our subset, where n is the number of buckets. And typically we make n like an order of magnitude greater. So if we want to store 1,000 objects, then maybe n is equal to 10,000, just to reduce the number of collisions. Next, we come up with some function that takes an object from the universe and maps it into one of the buckets. So the only indices we have for the buckets are 0 up through n minus 1. All right, so what might that look like? Oh, and then this last part, if we want to index something into the array, we just use our hash function, we pass in the object, and that gives us our index into the underlying array. So let's say we have the entire universe, and we have an array with n buckets, and here is 7. What we would do is we would take an object for our universe, pass it through the hash function. The hash function, for example, like djb2, gives us an index into our array. And we can do that for a bunch of objects. And these objects we actually have stored in here would be our subset S. So the question is, what happens if we have another object? So we've stored X, Y, and Z. We have another object A. We pass A through a hash function. What happens if it wants to be stored in the exact same location as something that's already in the hash table? And that will be the subject of the next set of videos, where we talk about collision resolution.